Okay, my friends, the good news about sections 3 and 4 is there's no more calculations. There's not really any more big new stuff to learn. 10.1 and 10.2 were huge. Confidence intervals and significance tests were huge ideas. This just kind of puts some more context to it. I'm going to combine them and just hit the high points. Listen closely. You need to read 10.3 and 10.4 because to put every single bit of information would take a lot more video than I'm going to do right now. So you need to read 3 and 4 before we have our test. So here are the big ideas behind 10, 3, and 4. First of all, significance level. We usually use what we call alpha equals 5%. Now, because we use that one so often, it can make you think that there's some sort of magic about 5%, some sort of cutoff level. Um, there is nothing magical about 5%. There's not really anything special about 5%. Why do we always use it then? Well, as your book says, before you had a calculator that would do this at any, give you any z-score you need, there used to be tables where they would give you the 1% and the 5% and the 10% z-star values that let you, calculate at those fixed levels. Now, from that, we've kind of used 5% as the magic one. It's just the most commonly used one because I guess we think, 1 out of 20 is rare enough to where we consider that to be the cutoff point. If the probability of our result is less than 5%, we just kind of go with that. Just realize if P is 5.1%, you're not going to reject the null. If P is 4.9%, you're going to reject. So you could basically get the same outcome, almost the same, and at some point you say either reject or don't reject. In real life, if I get a 5.1, I'm pretty sure I'm going to test it out again to make sure that my results agree. But calling somebody a liar because you got 4.9 and calling them truthful because you got 5.1 doesn't really make sense in the real world. I'd like to read a sentence in your book. The way they say it is this: there is no sharp border between significant and insignificant, only increasingly strong evidence as the p-value decreases. So as p decreases, we get more evidence against the null hypothesis. Okay, so just keep that in mind. I know 5% is the number we're going to use, and the questions you answer should say test this at the 5% level. You could test it at any level you wanted, but that's just the most common one. But just don't feel like 5.1 is awesome and 4.9 is terrible. Okay, number 2, unlikely events will happen. Let's stick with this 5%. If it's 5%, then that means 1 out of 20 is going to be a mistake. So there's a good example. A good problem will work in class about 500 people trying something, just sheer luck, and the best ones should we conclude they were awesome at this. So let's say, I like gambling examples. So let's say, 1,000 people enter a roulette tournament. Okay, so roulette is purely luck, the way the ball falls, the marble in the colors. 1,000 people enter a roulette tournament. I don't even know if there are roulette tournaments, but sounds fantastic, so we'll go with that. Let's say 7 people do so well that their p-value would be less than 0.01. So they were significantly awesome at roulette to the level of top 1%. All right. So they did great. So are they more skilled at roulette than the average person? Well, in a game that involves absolutely no skill, no, they're not more skilled. They just got lucky. All right. There have to be values that are unlikely that will happen. So think about this. P is less than 1%, means they're the top 1% of the finishers in this tournament. Well, what's 1% of 1,000? All right, that's 10, correct? So we would expect even more than 7 people to do that well. Okay, by the nature of P equals 0.01, that's saying best 1 out of 100 or best 10 out of 1,000. So if 7 people got over that value, it doesn't mean they're skilled. The question in your book is about ESP, like, testing people out to see if they're psychics. Should we conclude that the top finishers were psychics? Well, of course not. Somebody has to get that lucky. Rare events will happen. If you use a 5% level, then 1 out of 20 times you're going to be wrong. So if you say, hey, best person in the roulette tournament, you are very skilled. I want to hire you to bet all my money on roulette. That's a huge mistake. What they are is the most lucky person in this particular tournament. Next time, they have just as good a chance of stinking it up like everybody else. Okay, another idea, practical significance. Let's say, I'm going to just make up a quick example. Let's say that everybody who gets the flu is sick for 5 days. And let's take a sample of 1,000 people and give them all a new treatment, some sort of medicine for their flu. And those people have an average, I should use X bar, of 4.8 days. Okay, now you go through all the significance tests and you're trying to see, is this treatment significantly helping them get better faster? And you do all that and you go through it and you get the p-value of 0.0162. So basically you get a 1.6% chance. So think about what that p-value is saying. Assuming the medicine doesn't work and their average is 5, just like everybody else's average, then the probability that we get an average of 4.8 is only 1.6%. So we reject the null. This is a very shortened version. We reject the null and we conclude the medicine helped speed up their recovery. All right, nothing is wrong here. Okay, let's say this medicine cost you $1,000. All right, it's going to help. Some people who are really sick might pay $1,000 to get better. Would you pay $1,000 to get better? All right, it's absolutely, it's not absolutely, but we are very, very, very certain it's going to make you get better faster. Well, think about it. These people who took the medicine, they did get better faster, but they only got better faster on average by 2.2 days. So that's 1/5 of a day, and a day is 24 hours. So whatever 1/5 of 24 hours is, let's call that almost 5 hours. You can take this medicine. It might be very expensive, and I'm pretty darn certain I can help you get better 5 hours sooner. But you are going to get better 5 hours later anyway, so would you pay a lot of money for it? This is practical versus statistical. This is statistically significant. All right, this p-value is statistically significant, meaning it's very unlikely to happen, assuming the medicine's no good. So because it's so unlikely, I think the medicine is good. However, who cares? 5 days versus 4.8 days. It's almost the exact same anyway. So something can be statistically significant without being real world significant. So keep that in mind. Another topic of discussion of significance tests. All right, type 1 and type 2 errors. Type 1. There's two things that can go wrong when you're doing a significance test. Every time you're going to make one of two decisions. Either I reject or I fail to reject the null. And either one of those could be wrong. All right. All of stats, this is based on inference. This is based on making our best guess, our mathematical best guess based on the sample we took. So a type 1 error is going to happen whatever alpha is percentage of the time. If the null hypothesis is true, 5%, if we're going with 5% of people are just going to be the unlucky ones who got a bad sample and who reject the null when it in fact was true. All right? That's what the 5% means. That's what we do with a null hypothesis. This is the likelihood of getting something we got if in fact the null were true. Okay? It's possible 5% of the time. All right? A type 1 is when you reject the null when it's true. Okay? And that will happen. Let's just put it like this. The probability of a type 1 equals alpha. If you're testing at the 5% level, then 5% of the time you're going to get a result that low, even if it's true. All right? That's what the p-value does. It gives us, assuming it's true, assuming the null is true, it's the probability that we get a result as far away as we got. Well, just by that definition, alpha percent of the time, you're going to be wrong. All right? If you want to test at the 99% level, or excuse me, the 1% level, then there's only a 1% chance you're going to mess up. But if you want to do a 10% level, there's a 10% chance you're going to mess up. All right? Whatever that, this is a very common question. What's the probability of making a type 1 error? What's whatever level you are testing at? If you're at 5%, 5%. The most common answer to this question is 5%. Okay, the other thing that you can mess up is you can fail to reject the null when it's false. Notice I'm still not using the word accept. We never quite accept anything. We just don't call them a liar. Okay, so let's say it's false. The battery claims to last 10 hours. I test a bunch of them, and I get 9 and 9.5 hours. But that's not far enough to reject, when in reality, their average wasn't 10 hours. Okay? We fail to reject when it's false. And usually one of these will be worse. Let's say you are testing the amount of some sort of chemical in your food. I think, okay, there's this much of this chemical is allowed to be in my food. I do a study. I take some samples, a bag of chips or whatever, and I reject the null. The null says that there is this much. I reject this and say that there is more. All right, I say there's too much of this chemical in the food. If that's the case, then I throw all the chips out because I think they're bad. In reality, the null was true. They were okay. So this is like throwing away good chips. We're going with chips because I've got an old example. Now, you don't want to throw away good chips as the chip manufacturer. You're wasting money. But think about the other one. You fail to reject the null when it's false. All right, the null is false, meaning there is too much chemical. It's not right on track. All right, you don't reject them, you sell them to people. You sell poisonous chips. This is more dangerous in this case. Sometimes type 1 is bad, sometimes type 2 is bad. They're both mistakes, but sometimes one is way worse. All right, you're better off throwing away good chips than you are selling poisonous chips and getting sued by everybody who ever ate a bag of your chips. All right, that's type 1 and type 2. We aren't going to, maybe never, maybe not very often, I'll let you know for sure later, calculate the probability of a type 2. But the term you need to know is power. Power is basically your resistance to type 2 errors. It is 1 minus the probability of a type 2. And because we don't calculate type 2, we're very rarely going to calculate power, because we very rarely will calculate type 2. But what you should know is if you want to increase your power, the big way to do that, which is always the case, is larger sample. And the other easy way to increase your power is to increase alpha. All right, both of those will increase power. We can talk more about this one in class. I don't want to spend a lot of this video time on it. But power is, a high power means you're not likely to commit a type 2, which could be very bad if you're a poisonous chip seller. But if you have a larger alpha value, think about that. If you are at 5% instead of 1%, if you're at a 1% level, you are going to reject very few. So if you reject very few bags of chips, you're more likely to put them out into the stores with some poison in them. If you do 5%, you're more likely to catch that mistake and to reject the batch altogether. But in going from 1 to 5, you have a higher probability of a type 1 error. So it's kind of a trade-off between 1 and 2. All right, so what you do need to know, and these are kind of issues that, you need to know definitions. We aren't going to do a lot of calculations based on them. But you absolutely need to know that a type 1 is rejecting the null when it's true. You need to know the probability of that happening is whatever alpha is. You need to know that a type 2 is failing to reject when it is actually false. And we'll come back to power as needed. And that'll do it. All right, so these are just some more practical ideas. And like I said, you need to read 3 and 4 because I can't get nearly enough info into this video before you need it for the test. So read those. Let me know if you have any questions. See you in class. Young out.